Okay, so we're going to continue moving through semiconductor devices involving light, and today we're going to talk about light-emitting diodes and solid-state lighting. Solid-state lighting is basically light-emitting diodes, it's just another term for that. The photo that we have to start here is my favorite photo of this entire course. I've got a semiconductor diode here, and you can see it's in action because it's emitting light. Here's your wire contact. I can see there's doing some current spreading with some gold fingers that are spread out here. You can see the orange light emission coming out of this thing. The beauty of this too is that if you look at the device, you've got your N-type region and your P-type region, and you can even see that in terms of the emission intensity differences here and the outcoupling differences here in terms of this line down there. And so you can really see the device structure come to life. Now, how long have LEDs been around? Well, the first report of electroluminescence was from silicon carbide, and that was by Sir Henry Round in 1907. Note that this was not really a LED as we will talk about it today. It involved high voltage and some light emission that was very dim. It used a Schottky diode, but it's not quite the PN junction diodes that we'll be talking about today. So at this point, we are in pretty good shape because we already know how to calculate light emission for a semiconductor. We also know that even though all semiconductors can absorb light, as long as it has larger energy in the band gap, we know that only direct band gap semiconductors emit light by electron-hole recombination. When you talk about this recombination, it's a rate. So if it's a rate per unit second, then it means we also have a lifetime. And remember, there is a doping dependence on lifetime, which we have with this equation. Basically, dopings go up, lifetime goes down. And we also had this recombination factor, alpha R. And a key thing I want to mention here is that alpha R is different for radiative recombination, something meaning light-emitting recombination, gallium nitride, for example, versus non-radiative, like silicon. And that makes sense because if you think of, gallium nitride, we use it as a light-emitting material, right? But theoretically in gallium nitride, it could recombine and generate heat, which is non-radiative, or generate light, which is radiative. And that shows you that generally emitting photons is faster in terms of this recombination coefficient than generating heat in a really good light-emitting material. So materials like gallium nitride, most of the recombination is going to go into light generation once it's made high quality. That also assumes, though, there aren't a lot of defects. So if you grow a semiconductor and there's lots of defects in it, then those can dominate the recombination, and those can basically cause recombination just occur as heat. So the key point is that this alpha R is really an average of all the effects that can cause recombination: generate heat, recombine at defects, or generate light. And for an LED, you want the recombination coefficient for light emission to be dominant over the other ones. Again, which semiconductors are used for LEDs? We've covered this. We will focus primarily on the 3-5 semiconductors, gallium nitride, aluminum gallium phosphide, and things of those nature. So, if we know we're going to use nitrides for semiconductors, let's already ask ourselves one of the questions that is related to nitrides. First off, you'll notice that the nitride system, aluminum nitride, gallium nitride, indium nitride, you have to add indium nitride to basically shift your band gap energy down in towards the green and the red. And so if you use just gallium nitride, we're out in the ultraviolet. This is the emission wavelength, right? And this is band gap energy. So what you typically do with gallium nitride is that there are no gallium nitride substrates, and you've got to grow on top of a substrate, P and N type layers, to build up your LEDs. And if there's no gallium nitride substrates, they typically use silicon carbide. Well, this axis here is the lattice constant, meaning the spacing between the atoms. And so silicon carbide works okay, because you can see gallium nitride's over here. And so if I'm growing a crystal of gallium nitride on silicon carbide, I can make it happen. Even though they're not going to perfectly match up in lattice constants, I'll get a little bit of strain, but it'll work. The problem is you try to use gallium nitride and you shift towards from blue to green. Green's over here. I have to add more indium nitride, And now my lattice constant difference is much greater. And so what you'll find is that green LEDs are a huge challenge and typically lower efficiency because the semiconductors become highly defective because you're trying to grow a semiconductor with crystallinity and lattice constant of 3.4 angstroms on a substrate which is much smaller in the spacing. So you get tons of defects which gobble up the recombination instead of light emission. Furthermore, going out to the red is simply not possible with gallium nitride, indium nitride systems. The diodes become very inefficient at that point. So then you switch to a different material system like aluminum gallium phosphide instead of nitride, which has band gaps over in this range, and has band gaps in the range of the red through the infrared. So, how do we predict LED behavior? Do we need to rederive everything? Well, the answer is no. We just use the regular diode equations we had. Here's a question. Would an LED emit in reverse bias? Don't even think about this question. Think about it practically, because you know that in reverse bias, your reverse saturation current is absolutely tiny. So even if you did get a little bit of recombination leading to emission as carriers drifted to the other side, it doesn't matter. Who cares? It's such a tiny amount that it's totally impractical. It's orders and orders of magnitude lower than the forward bias. So speaking of forward bias, let's take two diodes, okay? And you could either reverse bias and forward bias it, but let's do the forward bias case. And let's assume one is an LED. So let's take two diodes just like this, forward bias one, forward bias the other. One is an LED, one is not. At 20 milliamps, which one's going to be hotter? Well, the one that's going to be hotter is the non-LED diode because all of its forward bias current will be electrons going over here recombining in heat, holes going this way recombining in heat, whereas for an LED, that recombination would result in photons which would leave the LED and take that energy out of the LED. And so you could run it at higher current without it overheating. Now let's start to look at how we specifically design a good LED. So I'm going to start to design a good LED, and you'll notice something common with solar cells, that the first thing I think I might do is I might make a thin N+ layer at the top here. So this is a gallium arsenide LED that will emit in the infrared. So I make this thin because that helps me get light out, right? Because if I made this too thick, the emission could be reabsorbed by the semiconductor. Because the emission will be greater than the band gap energy, right? If I've got a band diagram and I have an electron recombine with a hole and I get a photon, by definition, that photon has energy greater than the band gap energy. So that same photon could also be reabsorbed to generate electron-hole pairs. So I want to make this layer as thin as possible to get the light out. But there's a couple problems with this simple design. The problems are as follows. First off, the emission layer here ends up being very close to the surface here. And if you think about the surface, that's the edge of the semiconductor, and at that point you've got a bunch of bonds which are just left completely open because there's no more semiconductor at that point. So the semiconductor is totally defective at the surface because the crystal ends there. So as it was expecting to keep having bonding with continuous semiconductor, you've cut it there, and you've got all these bonds that are unformed, which are defects, which can gobble up emission. And so what happens, if I make this layer too thin here, quantum mechanically, my emission energy can then couple to the surface and recombine non-radiatively. And this is a big effect if you have your emitting layer too close to the edge of a semiconductor device. So that's a problem. The other problem is that for light emission going to the back here, I still have this thick p-type layer which will absorb light, right? This is thick, and so the photons can still be absorbed at the backside and I can't get those out. So at best I'm going to get half of my light emission. So the question is, how can we fix this and move to a new design? Well, the answer is a double heterojunction LED, meaning that I've got two heterojunctions, I've got a heterojunction here between wide bandgap semiconductor and narrow bandgap semiconductor, and another heterojunction here between narrow bandgap and wide bandgap. Meaning that heterojunction, these are two different types of semiconductors. They're not gallium arsenide. This is aluminum gallium arsenide. This is aluminum gallium arsenide. I still have P and N type regions. Let's see what this bought for us though. Okay? So if I look at a band diagram, what happens here is here's my wide bandgap aluminum gallium arsenide, it's N type. Here's my wide bandgap P type region here. Okay, I've started to forward bias this so the Fermi levels no longer line up. I've got my narrower bandgap gallium arsenide right here in the center. Electrons go this way, holes go this way, they start to recombine here. And two things have happened. First off, the light emission coming out of this layer here can easily get through the N and P type materials around it because they're wider band gap. This photon has energy for this band gap, which is not enough to be absorbed by this semiconductor here or this semiconductor here. So my issues with absorption in the P and N type regions outside of the emitting area have been resolved. The other thing that this does for me is that I can now make this thicker because I don't have to worry about getting the light out of this, and that keeps my emission layer further away from the surface here, so I don't have to worry about quantum mechanical energy transfer of the emission to the surface, which would just recombine as heat at the surface. So this solves both those problems. Last thing you'll note here is they make this the emitting layer, they make P minus gallium arsenide, meaning it's really lightly doped where the emission occurs. Why do they do that? Well, remember, when we talked about light emission for semiconductors, we said that defects, like you have at a surface, or defects inside the semiconductor could dominate the recombination and cause the recombination to just generate heat. Well, what is a bigger defect than taking a perfect semiconductor like gallium arsenide or some other semiconductor and putting dopant atoms in it? Dopant atoms are actually defects. They don't fit in the right size. They generate charge. They are actually defects if you think at it from a semiconductor standpoint. So typically for LEDs, your light emitting regions, you make them lightly doped because the dopant atoms themselves can act as recombination centers or defects to promote recombination that is non-radiative and which just generates heat. In terms of voltage requirements for LEDs, that's also easy. This is diode voltage versus diode current versus diode voltage for a bunch of different semiconductors. And so you can see as you increase your band gap energy, your voltages required to turn these diodes increases because you have to overcome contact potential. And so you can quickly see that you can get your emission wavelength for a diode, and that's going to somewhat track with the required turn-on voltage for the device to kick on. So, how efficient can a diode be? Well, there are three key things we need when you calculate performance in terms of efficiency for a diode. The first one is called internal quantum efficiency, meaning we don't want heat, but we want photon emission. And how you measure that is if I inject X electrons into the emitting region, how many of those will recombine with holes and give me photons out? So I only need to track the electrons because I assume if I inject an electron, it's going to recombine with a hole. So I'll just keep track of the number of electrons versus the number of photons emitted. That is my internal quantum efficiency. Now you can see here's a plot of internal quantum efficiency versus wavelength. And you can see what I said on the previous slides, that as you go from violet to blue to green for the indium gallium nitride system, the number of defects builds up as you try to make green semiconductors with the nitrides, such that the quantum efficiency goes down because of all those defects causing heat generation but not photon emission. Hence my quantum efficiency here, internal quantum efficiency, goes down. And you have the same problem with the aluminum gallium indium phosphide system out here for red. As you go in this direction too, it becomes inefficient. So green LEDs have actually been one of the biggest challenges in semiconductor diodes for especially solid state lighting. The second thing we care about is injection efficiency, meaning that if we have something like a double heterojunction LED, I want the recombination to only occur in the active region. Okay? meaning that only where the band gap is set to the right emission wavelength. So let's say I have a double hetero junction where I've got wide band gap UV on either side of the light emitting region, which is blue. Well, if I get recombination out in the UV emitting areas, the wider band gap, I can't see that with my eye, right? So that does nothing for me. I want the recombination to occur in the right part of the diode with the right band gap, which is the emission that I'm after. And so this injection efficiency, gamma, is the percent of electrons recombining in the active region with the right band gap for the emission you're after. The third bit to efficiency is outcoupling efficiency, and we'll go into details for that on the next slide. That basically is how many photons get out. So, how many photons are generated inside, how many photons escape. Most of them, you'll see, it's difficult for them to escape, so this, of course, is less than 1 in terms of efficiency as well. Let's do a simple calculation. Let's calculate the internally generated optical power, not escaping, just the internal generated optical power for a red LED operating at 1 milliamp. So, we know that optical power, watts, is joules per second. So I'm going to take the joules per second, I'll put joules here and seconds here, and I'm going to multiply those by coulombs over coulombs, right? So I just basically broke this out and said, okay, I'll make this coulombs over second and this joules over coulomb. And of course, if I multiplied this back out, I would end up with joules over seconds because the coulombs cancel out. So I'm just expanding this and adding units in there. Well, this helps me because if I drive this with 1 milliamp, that's my coulombs per second. So I'll put 1 milliamp in there. How do I get joules per coulomb? Well, for red light, I know that my energy is 1240 over lambda, right? So I can put that in here for my joules. And if I need my coulomb, I can get my internal quantum efficiency, which has units of coulombs in the denominator here, which is exactly what I want to get per coulomb. So I'll do that. I'll basically plug in 1 milliamp. That was my starting assumption for current. 1240 over lambda, red emission, 650 nanometers. And if I'm at 650, I'll assume that my quantum efficiency is 50%, so I'll put that in there, and I calculate that I get 1 milliwatt of optical power out. Another way to calculate this answer and get the same answer is pretty simple. Let's say I've got red light emission, which is at 2 electron volts. How much voltage does it take to turn on the diode? Well, it's going to take at least 2 volts to turn the diode on, right? How much power is consumed then if I've got 1 milliamp and 2 volts? Well, that's easy. I've got 2 volts times 1 milliamp, which equals 2 milliwatts, right? Sorry, my watts is falling off the screen there. I'll right here. So I've got 2 milliwatts. That was easy to calculate. Then you say, okay, of this electrical power, how much of this is efficiently turned inside the device into photons? Well, my quantum efficiency is 50%, so 2 milliwatts times 0.5 would give me the same 1 milliwatt answer. And again, this was internally generated optical power. Now let's look at how much of it gets out, and you'll be surprised that it's difficult to get all the light out. So, let's calculate the total external quantum efficiency for an example gallium phosphide LED. How we'll calculate that is the injection efficiency, internal quantum efficiency, and the outcoupling efficiency. So let's assume our injection efficiency is 1, because we could design the LED to do that, and you'll see how we do that a little bit later. Same quantum efficiency internally, 0.5. And then my outcoupling efficiency is 0.084, which really kills me and gives me a net efficiency of only 4%. So why is the outcoupling so poor? Well, there's 2 reasons. Semiconductors typically have a high refractive index. So anytime you have light going between a semiconductor and another material with a different refractive index, you get Fresnel reflection. What's Fresnel reflection? Well, if you look at a window, you get a little bit of reflection off the surface, right? That's Fresnel reflection. So basically you can calculate it as follows. The percent reflection you get that is not transmitted through refraction between 2 materials of different refractive indices can be calculated by the difference of the refractive indices squared over the sum of the refractive indices squared. The other thing, and this is the big one that really hurts you, is total internal reflection. So if you take Snell's law and you keep increasing your incidence angle, at some point Snell's law predicts that your refracted exit angle becomes 90 degrees, which means that it's actually internally reflected at that point. So if you keep, if I had light like this, it would be like this, right? And then I had light like this, it would go straight through. But if I keep increasing my angle this way for the incidence angle, eventually it becomes 90, which means it's totally internally reflected. And so I can easily calculate using Snell's law, set the external angle to 90, and then solve back for critical angle as follows. So, knowing that, we can do a simple calculation, and you'll see that given critical angle, if you're only within certain angles here will the light get out. Any other angle outside of this, the light ends up getting totally internally reflected. So any of these cones, if the light is outside of those cones, the light is totally internally reflected back out. If it's inside the cones, it gets out. Okay? And so you'll see that if you could do a derivation on this, and I've done it before, but I won't do it here, that each cone, if you use this equation, you can derive that the percent of light getting out at each cone is 1 over 4 times the refractive index of the LED squared. So, how do we get this low efficiency here? Well, let's take our Fresnel reflection, which for gallium phosphide, which has a refractive index of 1.34 and air refractive index of 1, put it in here, you find you get 70% light out, even if you're in the cone, because a certain amount of it gets reflected back, just like you see your reflection in a window pane of glass. Now, critical angle for this is 17 degrees. You can calculate using this equation, which also, if you calculate this way, gives you only 2% at each cone. Let's assume we have 6 sides to get the light out. So 70% Fresnel reflection, 2% times 6 sides equals 8.4% of the light getting out. So the question is, for this LED-shaped inverted pyramid, why are they doing this? Why didn't they keep it a box like this? Well, the reason why is that if I have a box-type geometry, if light is stuck within the critical angle, it will just keep bouncing around and be stuck inside the LED. It won't be able to escape. However, if I change the geometry like this, every time it hits a curved surface, you could say, oh, now it's more normal to the surface, it can get out. And if it can't get out, every time it hits the curved surface, it slightly adjusts the angle until eventually it finds an angle where it can escape. And so that's why they use this inverted pyramid geometry. It's to help get the light out and to avoid this effect of total internal reflection. So at this point, take a break, do this review. You should be able to answer these questions, and then there's one more part to this lecture.